Thank you. I could have built 100 models with using H2O in this short time. Delay. Sorry for the delay. So I'm going to be talking about fraud prevention using deep learning. This is the outline of my presentation. A little bit about me. I'm a data scientist at PayPal, primarily working on the area of risk management and fraud detection. Prior to that, I have years of, maybe decades of experience developing server-side software. I also have PhD in computer science, where I specialized applying machine learning and natural language processing. So the outline about PayPal, you've heard some presentations from previous presenters. I'll a little bit talk about what we do at PayPal and specifically our risk management group, which deals with fraud prevention. Also, I'll talk about why I chose deep learning and H2O for solving this problem. I'll go over my experimental setup, some of the lessons I learned using H2O and deep learning. Share some results. You'll get some quantitative numbers on real data sets from this presentation. So also conclude with some of my thoughts using H2O and deep learning. Okay, PayPal, I think most of you should know PayPal, but some of the recent, if you're not up to date with the recent, what PayPal is doing is we have over 150 million members, active digital wallets, and we are operating in over 200 countries. We have a deep relationship with every customer segment, and our core competency is in risk. And the reason we were able to do all this growth is due to our incredible competency in the risk management side of PayPal. We are an innovative leader. This is some of the recent innovations. So the one on the left, the payment QR code is actually it's for we were started off as an online payment company. We also going into the offline world. This is actually you will be able to use it in a store to buy any of the products in the offline world. And the next one is the wearable tech. That's also another recent innovation. So we also do a lot of innovation in the fraud prevention area, which is actually some of the key highlights of our what we do at PayPal in the fraud prevention areas. We have a state-of-the-art feature engineering. You can think that it is, we have millions of transactions dealing with the billions of dollars, and being able to detect fraud reliably and prevent it. We need these kind of state-of-the-art feature engineering. We have state-of-the-art machine learning tools, both homegrown and a lot of some commercial and some in-house developed. And we also have a lot of statistical models. As you can imagine, that the volume of scale we deal with, our server, the software and the infrastructure is highly scalable. We also have a superior team of data scientists, researchers, financial, and even intelligent analysis and security experts. So this is a little bit more of fraud prevention PayPal. Primarily, this is actually a kind of a fraud 101. We have three multi-layered way to deal with the fraud. The first one is the transaction level. At anytime a transaction happens, the online payment happens, we apply state-of-the-art machine learning algorithms and statistical models to detect whether it's a flag that behavior is fraudulent, so that we can prevent fraud before it actually happens. So we also employ more sophisticated models. So once the transaction goes through different stages, we employ further, again, machine learning based models, which where SLA is a little bit more, we have more time to evaluate the fraudulent nature of the behavior and act on it. So that way we can even, if there are fraudulent activities, we can reverse the transactions because of the multi-layered approach. At the account level, we monitor account level activity throughout the entire life stage of the account. We look for abusive patterns. Some of the simple examples, like you have been physically located in the US, but suddenly there is a payment happening in Australia, so we'll be able to detect IP-based or region-based anomalies. Those are some simple anomalies. The network level, for example, the fraudsters, what they do is that they collect money from several accounts and accumulate in a centralized account, which later on they move it to a further account so that they can basically eliminate the trace of their movements. So we have different sophisticated algorithms to detect these kind of account interactions. So fraudsters are increasingly complex. So some of the examples I showed you is quite simple. Obviously, in reality, the volume of the data which we are dealing with and the volume of transactions, it's not that simple. So we need something be able to model those cost nonlinear relations among the data, and we also need a cost-effective solution which is scalable. Obviously, scaling is actually if a solution is actually, we have a mission that if it is not scalable, it's not usable. So that's why I looked into deep learning. Why I chose deep learning is because is that you can see that most of the fraud behavior, the attackers are changing the activity patterns in almost in real time. So, for example, they can conduct a denial of service attack, and while the attack is going on, they can sneak into our system. So we need to be able to detect these behaviors in real time, and to model that, we need to have features and machine learning models to capture this relationship, which is not actually a human cannot be even to observe. So the deep learning actually has been widely employed in image video processing and object recognition tasks. So as to my knowledge, it is not applied to the area of fraud prevention. So that's why I decided to give it a try. And why H2O? I said that our solution, whatever we have for the volume of data we have, it needs to be scalable. H2O, that is one thing, is that it's a highly scalable infrastructure. I'll go a little bit more about some of the experience I went through. It's superior performance based on all the benchmarks results which they have published. Flexible deployment, which actually really appeals to me. I will go a little bit more detail on that. It works seamless with big data frameworks. So we have lots of big data technologies at PayPal, Hadoop, Spark, and all those stuff. So we want to be able to seamlessly work with those environments. And it also has a simple interface for data scientists and everybody to experiment on using this framework. So that's why I picked H2O and the deep learning. So on the data set, which started with, this is actually, it's a subset of the data to deal with fraud, which is, you can see that itself is 160 million records. This is a subset which is 160 million, but that's the scale we are talking about. Yeah, it's about 1,500 features, 150 of them are categorical. In the compressed data, it's about 500 gig compressed in the HDFS. Our infrastructure, the infrastructure which I used for this particular thing is 800 Hadoop cluster, which is running the older version of Hadoop, which is CDH3. Our decision to make is whether it's a fraud or not fraud. So we have all this data, we have all these features. So I want to see how can I do an experiment using H2O. So our first setup is that we have the cluster already there, and H2O has a fantastic R interface. In fact, I haven't written, prior to that, I haven't written a single line of, I've done a lot of Java code, but not a single line of R code. But you can see that by seeing the simple interface which they have provided using R, I switched to R for this particular work. I tried with this that R as a client, my very first, obviously, as with anybody who's using a newer software, it's a failure. It's unable to successfully operate on those the data set and the size of the data which I was talking about. The biggest failure was the H2O unable to form a cloud. So H2O infrastructure actually, if you look at it, actually the architecture is we have Hadoop cluster, HDFS, and H2O actually can start mappers as part of the cloud, and which means basically it's run as a. So let's say you want to process 100 gigs of data, you need to have enough mappers to load that 100 gigs of data into a map process. So you start the cloud as a mapper process, then you go and apply your machine learning, import the data and do machine learning models on it. But this was actually failed partly because of that H2O's need for memory being have to have upfront. They do work with if you have a disk and they use the swap space, but the performance really tanks when you start using disk. But the design goal of H2O is actually an in-memory data system. So obviously, if you don't have enough memory upfront, it's not usable. So I was not able to use this, but as actually some of the presenters actually earlier pointed out, we have different clusters where yarn-based, which supports multi-tenant, where we will be able to operate H2O in that environment. But this particular data set where we had is running in Cloudera's older version of Hadoop. So it's partly due to that, and also we have a limitation on as a single user, how much mapper you can ask, because it is a shared environment, we control resources on how much individual user has. So, unfortunately, I was not able to go much with this setup. And my next setup was that actually this is I think some of the earlier presenters also tried this particular approach, right? You have the Hadoop HDFS. So can I start a cloud outside this Hadoop environment? So basically, I had a 5-node H2O cluster, which is running on individual servers, but all the data is still there in HDFS in a compressed form. Again, R as a client, I tried this setup. Actually, this one also failed because this is partly because of my I didn't pay attention to the document. So they don't currently support snappy compression, which is actually been working with the Cliff, and he has given some suggestions to UC to extend it. Our data was all snappy compressed. We have a different process which actually creates this data, and H2O currently doesn't support snappy. So what I did was that I actually recompressed the data. The reason is that we have lots of data. The most optimally use the data, we have to keep it in compressed form in the Hadoop cluster so that it's usable for everybody else. So I gzipped data, and it's using the same setup. Again, it's failed. So but the first issue which I had was that the import was extremely slow. So for example, for 1 gig data, it was taking more than an hour to suck the data into H2O cloud. So that is actually one of the thing is that H2O the H2O is the rest of the process was highly parallelized, but the import process is not. It is on a single server. It's not parallelized. So it was using a single thread to ingest the data. That was actually done with. This is where actually the H2O team response really comes into play. I posted on the forum. Cliff immediately responded actually, and he looked at it and he investigated. Some of the issues which I have was that when I was doing all this stuff, PayPal actually we have a lot of sensitive information. We can't let the user log into our system to inspect it, or we can't exchange any of this piece of information data. So actually, Cliff and Arno, I'll go over later on, but they have to be intelligent about what is actually going on without actually me revealing about 1% of the information. They had to detect what exactly going on to be able to fix the problem, right? So in this case, Cliff figured it out that okay, that this is not this is the reason why it's working. He quickly turned around a fix which parallelized the import process. So it's the import actually fixed from 1 gig to the same data I could be able to ingest in 10 minutes. There are still optimizations worked around what type of disk we are using. So Cliff was getting much better performance on their one cluster. So I still have to. I'm working with them to investigate it. But there's significant increase in the import process. So this also failed. So okay, I imported the data. I tried to run a deep learning, again failed. What happened was that what is happening was this is where the data comes into play, right? When you're running deep learning, the first generation of the first one, so a few months back, 3-4 months back, which I started it, is that it was we had lots of missing values. So which means that 99% of the data had some kind of missing values. And H2O's, the deep learning, initially what it was doing, or maybe the deep learning process, I guess, it was skipping most of the rows. So eventually we didn't have enough data to train at all. So this is again, actually, I really have to credit Arno in identifying the problem. Again, I'm giving only, you can imagine that I'm giving you snippets of information. This is what the issue I'm having. And I can't give you the data, but go figure it out, right? Arna was able to find out because I put some statistics and give it to him. Oh, you know what? This is happening because 99% of the value you had missing values, and our first release is actually skipping all the values, even if a single value is missing. Single column is missing, you're skipping the entire row. So he turned around and improvements around it, imputing values if it is missing. So he added that fix, quickly turned around a fix for that. So that get to my next stage. So I have a Cliff's fix and a Arna's fix for treating with the missing values. Okay, so was I able to go to do? No. Again, deep learning was so slow. So, so what was happening here? There are several tunables within the deep learning thing. Is that one of the key ones was that they have a number of. There is a neural network-based iteration. There is a MapReduce-based iteration. So there is a key tunable called number of training samples per iteration, which is actually how many samples a single MapReduce can process. So that is there are several changes which Arno has since made after I tried it to be intelligently detect what should the number be, right? So previously those fixes weren't there. So you have to come up with a number, but this is a number. If you choose a number too small, then you'll have an incredibly long time to run your deep learning. But if you choose too high, you'll end up having an unstable model. So there is some intelligence involved, but Arno has had some changes since after I tried it out. So all this is there. So yeah, okay, sorry.
A very quick question. Cliff's fix and Arna's fix, are they specific to your implementation, or is it part of the product?
It is part of the product. Everything is actually, Arno didn't know me. I just posted on the forum. He gets this thing, immediately he responds it. He does all this part of the open source fixes, exactly. So yeah, we were communicating anonymously, so you can see that. So it keeps on going. So you know what? I guess you all had to be sit here until dinner time to get to find out whether I was finally able to run deep learning, right? Thankfully, no. So finally, I was able to get a setup which get to work. So this is actually there are several Arna's fixes, Cliff's fixes, everything is there, all going to open source. So just to get that presentation going, so I also instead of using all the 100 million records, I used 10 million, which is still quite a big with 1,500 columns compared to the standard publicly available data sets. So my split is 60-20 split. This is my experiment. This is where I started my this thing. So what I wanted to find out was that these are the parameters which I added. Deep learning has several parameters like number of hidden layers, number of neurons, several activation functions. They have this adaptive learning rate, L1, L2 recognition, so many parameters. So I want to drill down deep into that, which set of subsets actually work the best for on our data set. So vary the hidden layers actually. So you can see that the area AUC for 2, 4, and 6, and 8 layers, after 6 hidden layers, the performance actually kind of stays steady. So how depth the neural network for the data set is actually 6 was the right number. This is actually after trying hundreds and hundreds of models, finally this is the most stable I was able to find. In terms of varying the number of neurons in the hidden layer, so you can see that this actually is, even though it's incredibly flexible and simple to use with H2O because they provide the grid search. So you can vary these parameters quite easily and let the tool tell you how fast what is the best number should be. In terms of activation functions, I tried out all of them. The rectifier with the dropout yielded me the best performance. Let's see, subset of features. So this is actually really, sorry.
So how many features are in this subset?
1,500 features. No, let me get to the, so all of those results are using all the entire set of features. So now what I wanted to do was that, first of all, can I do with less? right?
Basically, my real question is, what is the heuristics of number of neurons compared to number of features? Right?
What is that?
Records to free parameters.
The free parameter. So
How many training records do you have as a ratio to weights in your journal?
And the neurons, right? So if you have hundreds of neurons, how
Right.
many features are they supporting? Would you need 100 neurons if you have just a couple features? Or how many neurons would you need if you have 1,000 features? That's really the question.
oh, so that number, I don't have that handy. Actually, I can look up the information.
But the features are like in hundreds, right?
Features, no, the total number of raw features is 1,500 features, right?
So you have feature subset what? How many features are in this?
So all of these results, actually, if you look at it, go back, we have 1,500 features total. So then what I wanted to do was, can I use less than those 1,500 features and try several subsets? So that is because the reason I did that was that I wanted to see, because we spend a lot of money in feature re-engineering, which is really huge. I wanted to see whether can we not invest in some other features, because one of the power of the deep learning is it's able to inherit or derive all those nonlinear features, right? So that's I wanted to try it. So in fact, one of the things which I cited was the subset 7, which actually didn't have that many nonlinear features, yielded the worst performance, right? 0.75% AUC. So my next step was, can I improve this, the subset 7, which didn't have that many nonlinear features? It still had this thing. Can I improve with the deep learning? Which is actually, in this case, I wanted to try is that use a subset 7, can I improve my AUC just using deep learning, right? So I tried with the 6 hidden layers and 600 neurons in this. I was able to increase AUC by 11%. So this shows that deep learning does work on this size of data.
For the original quintillion transactions, did you have a label what's fraud and what's not fraud?
Yes, we do have it, yes.
How did you get that actually?
Oh, there are several intelligence around it, so I can't go into the details, but yes.
So how did you train the deep learning one layer at a time?
Like
check.
and then the next one, the next one.
Thought H2O couldn't do that yet.
No, yeah, go ahead.
Yeah, at this point, it's all or nothing. So you train the whole network at once. So it's possible to train an 8-layer network, as we just learned, so from scratch. That's with the adaptive learning rate. It's per neuron, per time step. It's all adaptive, so it figures it out itself.
That is one thing I want to emphasize with the adaptive learning rate with Arno has, is that that is one parameter I didn't have to touch it. That is the beauty of H2O, so it is adaptive. So. And also did one more testing to see the temporal robustness of deep learning, whether it is, you train on 1 week, how often you have to update the model. So you tried on different tests. You can see that it's temporally robust as well. Within 1% performance difference, I was able to see that the AUC stayed pretty steady. In conclusion, actually, I already went over all of this. Actually, some of the lessons in the interest of time. Actually, so I do want to convey my thanks to Arno especially, and he has done a lot of fixes without knowing me. This is the first time we are meeting in person. So I want to thank him, and also Cliff and rest of the H2O's team for a fantastic support. Thank you.
Thank you, Venkatesh. We have time for a question or two. Here we go.
As part of your final solution from downsampling from 160 million records down to only 10 million records, did you use any type of downsampling strategy to rebalance the zeros and ones? Was that also part of your reason
actually, I didn't want to
downsample?
downsample it, mainly because of my current server configuration. We don't have enough hardware to run through deep learning, so that's the reason. But we didn't want to. I'm continuing to work on the entire. But yeah, I did do a downsampling.
Just to clarify, deep learning doesn't require more memory if you have more data. It's just to store the data. That's what needs memory. So the model itself doesn't get bigger. It just takes longer to process all the points. But I would be surprised that it wouldn't work. So basically, as long as it fits in the memory of all the machines, it's fine.
Correct.
There's one default option that says replicate training data. And per default, it does that. That means every node gets all the data. And in your case, you have so much data that wouldn't fit on every single node. Then you can turn that replicate training data flag off. And every node only gets a piece of the data. And at that point, I think the model will still be better. Averaging pieces of the data, there each has a model, and then averaging those might be better than subsampling initially. So you could try that flag, turn off, replicate training data, and then run it on the whole data set.
Sure.
Because if you have time for 500 epochs, then you also have time for 50 epochs on 10 times as much data. Right? And that might be just as good or even better.
This is actually want to say that when you ask question on something in H2O forum, Arnaud doesn't tell you, go try this. He just tells you the reason why something is saying this. So thank you for that. I think that is really informative. So.
There's a question in the background.
So when you try this, actually it's a deep learning question. So when you try these different amounts of training data on the different nodes, so does it then, every time it chooses a sample of the training data to throw into this different, so that you don't reproduce the entire training set on every node. So is it random then in each epoch?
It happens during the import, actually. So when you import a big data set onto 10 nodes, let's say, then each node gets 1/10 of the data.
That is correct.
And the default mode is that now deep learning transfers everything to everybody. So it's a lot of network overhead, actually, per default. And that's only done because normally your data is small and it doesn't cost too much to send all the pieces to everybody. But if you turn this flag off, it will actually train faster because it doesn't have to send everything to everybody. Everybody just has what it already has, right? Because the import distributed it. So if you turn this flag off, basically the training starts immediately. Everybody just processes its local data, has a new model. Everybody has a different model based on that local data. And it finds a local minimum on that data, basically. And then you average the models. And then you get basically generalization, and you get a model that has seen everything in a way. So it's not theoretically clear how good that is, obviously, but it's a heuristic that seems to work fine in real data. So we can definitely go from here and try that.
Sure.
But it should be even faster because it doesn't need to redistribute the data.
How frequently do you average all the models? Is it with every epoch, every backprop?
You can specify the number of points to process before you average the models and then send it back out. So that's exactly the length of a MapReduce step. And that number can be 1 row per node, or it can be 100 million rows per node. You can keep processing your local data without communicating and averaging. So the number is totally flexible. You can literally specify it to the one last row that you want. And if it's a fraction, if it's not a multiple of the data set, it actually just processes a random subsample. So it's almost like random forest where you sample some points. So let's say you say I want 20% of my data set to be processed per MapReduce step, then that's what happens. You sample 20%. The next time you sample different 20%. So it's almost like a bagging concept. Yes, one more question.
So you described the training part of the deep learning and neural networks. Do you also, when you do the classification itself, do you use H2O itself for classifying the actual events that you're coming?
I couldn't hear at all anything, sorry.
So you described that training part of your neural networks. So my question is that for the classification part, when you get the actual events, do you still use H2O in this phase, or?
Use standardization? What is
Classification, like for example, you're getting.
It is a classification.
You trained your network.
Correct.
You came up with your final, like trained model.
Right.
This is the time for the actual like classification. You're getting events. You
That's
want to
correct.
classify
So
them.
all my results are on the test set after classifying.
What do you use for the actual real-time classification? It's still H2O.
We're still working through the stages of what it takes to do a production deployment. This is on the offline.
Okay. So you haven't yet had the online part.
That's correct. Yeah.
Okay.
This is on the offline, but it is a data set which is a realistic data set. What will happen if you did end up deploying in production?
I see. Okay.
So we have different sets of data set for one for building model and one for testing it.
Okay. Thank you.
So most of these experiments are offline.
All right. Thank you again, Venkatesh.
Thank you.